So during lecture, some of you were advocating for a plug-in method when we were talking about infinite limits. And I made a couple objections to such a method, but upon thinking about it more, I realized that there's a way to make such a method work that supersedes those objections, at least in certain examples. So let's take a look at a particular example to get an idea of what we're talking about. So if we consider the limit as x approaches 2 from the right of this rational function, the first thing we would do is try to plug in to evaluate the limit. And what we get is 3 in the numerator, and if you evaluate the denominator at 2, you'll find that you get 0. Right, so we get 3 over 0, and so this is some kind of infinite limit. So the important question to address then is, well, which infinity is it? Is it positive infinity or negative infinity limit? And to determine this, some of you were advocating the idea that we should plug in a point that's close to 2 from the right in order to evaluate the sign of the resulting quantity, and that would help us decide between positive or negative infinity. So for example, the idea would be to plug in, say, 2.1, 2.1 is close to 2 from the right, into this function here. And so you get 2.1 squared minus 1 over da-da-da-da. And then if we can figure out what this number is, if it's greater than 0, then we take positive infinity. And if it's less than 0, then we find that our limit should be negative infinity. In response to this method, I outlined 2 objections. The first objection is that to compute this quantity here, which I've repeated down here, computing that accurately to determine the sign looks like it's time consuming, right? To do these computations and actually get a numerical answer looks like it could be costly. So that's the first objection. The second objection is that, well, how do we know that 2.1 is close enough to 2 to give us an accurate sense of the sign of this function near 2? So it's perfectly possible to imagine that perhaps f of x looks something like this. So I've outlined the graph of a function here where f of x takes a negative value at 2.1, but nevertheless the limit as you approach 2 from the right of f of x is positive infinity, right? So you have a positive infinite limit here as you approach 2 from the right, but f at 2.1 is negative. So the sign at 2.1 is not representative of the sign of this infinite limit. Okay, so those are a couple objections that could potentially hold and give you a reason to wonder whether this is a good method in general. But what I want to outline in this video is how you can make this method work if you're just willing to do a little bit of algebra ahead of time. So the way to make the method work is based on the simple fact that linear functions only change sign once. So you have a linear function, y equals mx plus b, and it can only, where it hits the x-axis, the 0 of the linear function, on the one side it's either positive or negative, and positive or negative forever after. In this case we have positive. And on the other side it's also uniformly of a particular sign, so in this case negative. So let's return to our example here. The way we're going to use this fact, so our fact is about linear functions. To use that fact, we're going to just factor our polynomials. We're going to make sure we factor everything so we can get down to just talking about linear polynomials, products of linear polynomials, and then we'll be able to use this fact where it's relevant. So our first step here is just to factor, and our numerator is x minus 1 times x plus 1 being a difference of squares. While in the denominator we have a cubic polynomial, but we notice we have a factor of x in each term. So that means we can pull that x out, and then we get a simple quadratic there, which we can also factor. And that factors as x minus 2 times x plus 3. Okay, so now at this point, we follow the method that we discussed in class. So you just analyze the numerator and denominator separately, and you analyze each of the parts of the numerator and denominator. So this x minus 1 term, that is approaching 1 as x goes to 2 from the right. This, we're just plugging in here, basically. So this is approaching 3 by plugging in 2. And the x term in the denominator, that's approaching 2. The x minus 2 term, that's approaching 0, so that's going to be the problematic one. And we have to assign a particular sign to that one in order to figure out whether we have positive or negative infinity here. And this 2 here, that is this term here is approaching 5. So in class, it was at this point where I encouraged you to look at this limit and to say, since we're approaching from the right, that x is greater than 2. But this is where our plug-in method is going to depart from what we did in class. So we're going to do something different instead here and do a plug-in. And all we're going to do is apply this fact here, because all we're concerned about is this linear term here, x minus 2, right? And we know that a linear function only changes sign once. And so this linear function, it's 0 when x equals 2, and it's going to have a particular sign on either side of 2. And that's the only time it changes sign. So we know we have a stable sign on each side of 2 here. And since we're on the right side of 2, all we have to do is take any number that's bigger than 2 and plug it in here, and that's going to give us an accurate reading of the sign. So for example, we can take 3, which is to the right of 2, and 3 minus 2 is 1, and that's greater than 0. So the fact that that's greater than 0 tells us we have a plus sign here. And you really literally can take anything bigger than 2, and that's going to give you an accurate reading of the sign. It doesn't even have to be particularly close. So this method here, it addresses both of the issues that I talked about before. Since we're only talking about linear functions, it's very easy to evaluate a linear function, and this method is not sensitive to how close your input is to the limiting point. You can really, as long as you're taking it on the correct side, it's going to give you the correct reading of the sign. Okay, so this avoids both of the criticisms that I outlined before. And then you wrap up as usual, so we just count the signs. Here in this case, we see everything is positive, so this is going to lead to a positive infinity. So the answer is going to be infinity here. Okay, so that's how you work this method, and I'll end with giving you a general outline. So here's the method in general. It's a plug-in method for infinite limits with rational functions. So you have a rational function as a quotient of 2 polynomials, and let's say we're looking at the limit as you go to a from the right or left, and you plug in a and you find that you get a non-zero number over 0. So that signals an infinite limit. So to determine the limit, what you want to do is, all that really matters is the denominator, actually. So you want to factor q of x as completely as possible. That's the polynomial in the denominator. And so in the example we did above, we were able to factor the degree 3 polynomial completely. If you have a quadratic polynomial, you know how to factor quadratic polynomials. In general, it's possible you could run into polynomials of higher degree. It's not likely, but in the event that you do, all you need to do is extract all of the factors of x minus a. So because q of x vanishes when you plug a in, that means it has factors of x minus a. And to extract those factors of x minus a, you can do polynomial long division, which is something you may have learned in high school. So what I'm telling you really only matters if your polynomials are of degree sort of higher than 3. So you probably don't have to worry about this, but in any case, that's what you want to do. Extract all the factors of x minus a as much as possible. And when you do that, then you're going to have your polynomial factored, so you have all the factors of x minus a that you've extracted, and then some remaining polynomial which doesn't vanish when you plug a in. Because if this vanished when you plugged a in, that would mean there was an extra factor of x minus a in here that you should have pulled out. Okay, so we have this situation here. And in order to calculate the limit, then what we have is our f of x is p of x over q of x, and our q of x is nicely factored here. And when we analyze as x goes to a, our numerator, being a polynomial, that goes to p of a, which is just this non-zero number we got in the numerator here before. And in the denominator, we have x minus a to the k. That's going to 0 as we go to a. So that's what we'll have to figure out. And this extra r of x factor in q, that goes to r of a, which is not equal to 0 because we extracted all those x minus a factors from q. And then to determine the sign here, you just have to plug into this x minus a to the k. And you plug in, depending on whether you're coming in from the right or left, just pick any number to the left or right of a, depending on whatever the type of limit is, and that will determine your sign there. And then you just simply count up the signs, what the sign of the numerator is, what the sign of this guy is, and what the sign of x minus a to the k is. Okay, so that's how the plug-in method can be made to work when you have infinite limits of rational functions.